The third and final presentation will be Field Bendable Thermal Composite Rebar by Roberto Lopez-Anido and Cody Sheltra. So Roberto is Malcolm G. Long, 1932 professor of civil engineering, member of the Advanced Structures and Composite Center at Maine. He's a structural engineer with 27 years of experience in design, mechanics, material testing, and durability assessment of fiber reinforced polymer composites for construction. Cody is a research and development program manager at the ASCC at the University of Maine. I know he's a graduate of the MET program at Maine. He's been at the ASCC. How long, Cody? 8 or 9 years as an engineer now? 10. Okay. So anyway, looking forward to this. And I think there's also, to go along with it, will be a special demonstration if I'm not wrong, right? Okay. So Roberto, you kicking this off? They're going to tag team the presentation.
So again, the title of our presentation, Field Bendable Thermoplastic Pultruded Rebar. And you may have seen the samples we left on the tables. I have some extra one here. If there's any table that is missing one, I'll be glad to hand one. Anyone has a sample? Anyone missing one? Okay, it's about this. So let's see what is this thermoplastic rebar. The co-authors we have here are Jacob Clark, who is in the background and actually will do the most interesting part of the presentation, a real-time demonstration of how the rebar can be bent. Cody Sheltra, the leader of the team who made this possible in the lab. We're going to talk more about this. And myself working with Bill Davis and other team members here in the Composite Center that came up with this idea and made it happen. Okay. We organized the presentation into 5 parts. So we'll kick in with the 2 components of innovation, how this could happen. Again, I'll talk a bit more about the rebar itself. We go then into the machine that makes the rebar. I'll talk a little bit more about developments, properties, where we are heading, and finally, the demonstration by Jacob. So we have here 2 components that were key to innovate, to make this product, to develop it. The first one is being at the right place. And what is this place? It's the Composite Center. Most of you have seen it. There are lab tours also going on this afternoon. And basically, it's a facility where we can prototype, test, analyze, verify products that are based on composite materials with a focus on structural applications in infrastructure, in marine, in defense, in energy, and beyond that. This facility that you have seen today has been expanding. I have a little anecdote. I came to Maine in May 1998. So do the math, a little bit more than 25 years ago. And the day I came here, I walked to where the Composite Center is, and there was a big hole on the ground and machine working on the excavation. That was when the whole thing started to be constructed. And on over 25 years, I've seen expansion plus expansion of the building, following the vision of Habib Dagger, the center director. And the next one is the factory of the future. And this is very important for this project because that is where we are going to be able to basically go to the next step with this technology. We're going to see what are the things we want to do in the future, but integrate this with large format additive manufacturing, with different processes that are automated in composites, with robotics, with artificial intelligence. The second component to make this happen is to have the right team. And how is a team formed? I mean, how is our team? Well, the key here is that we have staff, full-time staff, dedicated to work in the lab to make things happen, from getting the right materials, testing, prototyping, getting the results, the reporting. Cody is leading this team, faculty members like Bill Davis and I and other collaborators as well, that we are really interested in looking at what are the contributions we can make in science and engineering, training graduate students, advising them, getting thesis publications out, and of course, students who are really the reason we're doing this, okay, both undergraduates and graduate students. Again, put a team together has been key for this project. So a little bit more about the rebar. A very simple slide. That's probably all what I'm going to say about structural engineering today. The secret of concrete is the perfect marriage between 2 materials: concrete resisting compression, a reinforcement in tension, traditional steel, a simple beam under 3-point bending with a top compression supported by the concrete and the tension by the rebar, again, traditional steel. Now, the way beams work in concrete is the concrete cracks, and that's not bad, okay? If we are exaggerating maybe the cracks because we penciled them with a Sharpie and we went to larger deflections, but a good, well-designed reinforced concrete beam will have a nice cracking pattern, not really very visible, with very small cracks, so we don't want chemicals and water to get to the reinforcement. But the question is how to make these two materials work together through good bond between the tension reinforcement and the concrete, okay? How that can happen. And of course, we need a material that really delivers tension reinforcement. The problem with steel, number one problem, is corrosion, okay? And that is what we want to really overcome with the use of non-corrosive composite bars. The other problem, secondary, but is certainly to consider, is weight. I mean, when we are handling the materials at the site, having a lightweight material makes a big advantage. This has been, I would say, well addressed, and these issues have been tackled by the composites industry today through the use of FRP rebar made with thermoset composites. These are basically composites where there is a chemical reaction in the manufacturing process. The typical process used is pultrusion, and once the chemical reaction happens, the material is set. And you have a product that will look like this. The problem is it cannot be shaped to the needs that are at the construction site. Imagine you want to make stirrups for shear reinforcement, you want to bend at the site, you cannot do it, okay? And if you need to have prefabricated parts, you will need to account for all those changes in geometry at the plant. That makes the current technology on thermoset composite rebars not very practical. And this is exactly what we want to tackle with this product. I mean, at this factor here. Very general comparison of what are the options for non-corrosive reinforcement. Coating steel bars, using stainless steel, or using thermoset rebar. These are the options you have today, the menus options. They solve different problems, that's great, but not all the problems, okay? And if we go to the last column, and we look at the red items there, the thermoset rebar is not field bendable. It's expensive for custom shapes because again, you need to do it beforehand at a factory and cannot be recycled. When we overcome those factors? So here we go with the proposed technology, the thermoplastic composite rebar that can be bent at the field, can be adapted for different geometries, still has the advantage of being lightweight, sustainable in the sense that we can recycle this material. Okay? In fact, we were looking actively at recycling technologies. And here we cross a challenge because we really went over this. I mean, the problem with using thermoplastics, why this has not been done 25 years ago, is because there was not really a technology to make these materials that are more viscous, I mean, being able to properly impregnate fibers, fiber reinforcement like glass or perhaps carbon, okay, to make them work together. So what we're looking here is at a non-reactive thermoplastic technology that makes the fibers be well protective with the binder being the thermoplastic polymer, creating a material. If you look at the cross-section of the little rebars, you will see it looks like just one material. It's a well-consolidated bar, meaning that binder, that thermoplastic has properly surrounded, embedded all the fibers, making everything work together. So now Cody is going to tell us how this is made.
So when Bill and Roberto came to myself and our team a couple of years ago and had the idea to make thermoplastic rebar, as Roberto mentioned, one of the major challenges was we didn't really have a good way to manufacture it that would be scalable. We actually started by stamp forming or flat panel consolidating a flat panel and putting deformations into the surface, and we would rip them on a table saw or a water jet. And that was the initial generation of rebar we used to prove the concept and see that there was value in pursuing, but there was a major issue with it being that we were making it with a batch process and our press was only 5 feet long. So we looked into different manufacturing methods that we could try to use to make the rebar that you have in your hand or on your table And the most comparable manufacturing process that we settled on was pultrusion. Some of you may already be aware of what pultrusion is and what it's capable of. There's a little bit on the slide there. Pultrusion is a process that can basically make constant cross-section shapes at a continuous length. It's similar to extrusion, except you're pulling material through, so it's called pultrusion. You may even have pultruded pieces of components in your own home. If you have a shovel with a fiberglass handle or a step ladder, the handle and the rails of the ladder are pultruded. Structural members are also possible with pultrusion and many different things in between. You can essentially find a pultruded part in every industry. Roberto mentioned that there are challenges with thermoplastic pultrusion. So people have been attempting pultrusion since around the late 40s and thermoplastic pultrusion soon after that. But the major issue that's prevented it from taking off is the resin viscosity. So thermoplastic resins can be up to hundreds of times more viscous than thermoset resins. It's almost like comparing like a maple syrup consistency to molasses in some cases. So the reasoning that thermoplastics have a challenge in pultrusion is because in pultrusion, as you could see in the diagram there, you start with the red kind of dry fabric reinforcement, if you will, fiberglass, carbon fiber, as Roberto mentioned. And there's an impregnation stage where you have to get resin through that part, or you won't have a cohesive composite to work with. You'll end up with dry spots, which will cause failures or what have you. Thermoplastics don't really bleed through the fabric all that well. If you have a thick enough laminate of dry reinforcement, you're going to end up almost laminating the surface instead of penetrating the entire laminate, which leads to failure. There are thermoplastic resin systems that start off as a two-part and go through a reactive process, which are low viscosity. They do allow for some variation of thermoplastic pultrusion, but they're not environmentally friendly. They have a high emission rate, and even to the point where operators need to use protective equipment like respirators, even near machine. And they're very limited to specific thermoplastics, such as nylon, PMMA. You can't use any thermoplastic in that process. So we had the problem of the resin saturation or resin wetting to overcome when we went out to design our machine, and we solved it by ignoring it. We took out the resin saturation step entirely and started with a totally different feedstock. We're not starting with dry fabric and liquid resin like in pultrusion. We're starting with a thermoplastic tape, you may call it. They call them thermoplastic tapes, unidirectional tapes, pre-preg fabrics. There's tons of different names for different products, but they're commercially available feedstocks. They're used in compression molding in industries. Automotive parts are made from these. If anybody skis, ski boots a lot of the time are made from these. But what's unique about them is we have the fiber reinforcement, and we have a precise quantity of resin that we can tune and is measurable, and it's an off-the-shelf product you can buy. You can buy these as unidirectional tapes with all fabric in one direction, or different fabrics with weaves and different customization options. So we created a pultrusion line that uses this as a feedstock to bypass the resin saturation issue and turned the process into basically a simple heat transfer exercise. So dissimilar from pultrusion that starts with a liquid resin, goes through a chemical reaction and cures, we're starting with a solid resin in the tape format. We have to heat it, we have to shape it, and we have to cool it, which isn't necessary in traditional pultrusion. As Roberto mentioned, because there's no chemical process that's setting the resin, like in thermoset or the reactive thermoplastic pultrusion, it's non-reactive. We run this machine in the lab, in the composite center. No PPE is required. You can walk right by the machine. You wouldn't know it's turned on by any type of emission or anything like that. Yeah. So here's sort of the process that I'm describing here. So it starts off with a material handling system, typically called a creel in pultrusion. Nothing's too unique about that. That's what holds all of our tapes. Goes through the next section is essentially an alignment stage. If you have a complicated laminate that needs specific tape layers in specific areas, It goes through an initial heating zone, which actually isn't done in the die like in thermoset pultrusion, because we want the plastic to reach sort of a formable stage before it hits the die. And it goes into the dies, which start the cooling process in a controlled way. That configuration allows us to use different types of thermoplastics that Roberto will mention in a couple of minutes, such as amorphous structures and semi-crystalline structures. And after that is a final cooling stage, which is essentially just needed to bring the material down to a safe handling state, because the state where it is held together, which we refer to as the TG or going below the TG, is sometimes a little bit too hot to touch, but all of the cooling to make the cross-section stable is done in the die. And then there's a drive puller system. That's every pultrusion system has that. Benefits, it's fast and automated. When my team runs this, we typically run it with one staff member and one student to help them out. It's all electric. There's no PPE required that some traditional pultrusion and other reactive thermoplastic pultrusion requires. And because of the thermoplastic feedstock used, which is commercially available and customizable, we can really use any resin type and any fiber type that we're interested in. Just a quick overview of a couple of different CFM capabilities and future capabilities we're working on. So you guys have the rebar in your hand. That actually uses two processes to manufacture. Pultrusion makes a smooth rod. And the other process isn't listed up here, and we all call it something different, but it's essentially rotary stamp forming. Two molds rotate to create the thermoplastic surface. And since it's a thermoplastic, it can be reheated and reshaped, which enables a couple of other alternative options that we can add onto this pultrusion line, which may or may not be possible with thermoset pultrusion, such as roll forming, which is a steel manufacturing process, but when combined with our thermoplastic pultrusion line, it can allow us to make multiple shapes from one die, which dies can be quite expensive and hard to acquire. Filament winding is another method that we can use to make things like piping and hollow structures, and it's one of the methods we're going to investigate for creating the shear interlocking deformations on the surface of a smooth rod. And finally, curving is something that has been relatively elusive to the pultrusion industry. With the plastic resin we're using and the ability to field bend, like with the rebar, we could theoretically create curved structural members that can match unique structure needs. We're working on that now. All of these are future capabilities that are in process. Back to you. Yep.
Some developments on the rebar. This pyramid gives us an idea in terms of the options we have to select a thermoplastic material. The pyramid has 4 levels. When we go up, we have better quality polymers. At the base, we have the commodity polymers. At the top, we have the advanced engineered polymers. And this classification is based on the temperature each polymer can sustain in service that is related to the temperature required to melt the polymer in processing. There are also 2 phases to this pyramid. One is the amorphous side of the pyramid. The other one is the semi-crystalline. So you can see that at different levels, we have different acronyms here for polymer composites. You may recognize some of those. Looking at the top, for example, the semi-crystalline one are some of the highest performing aerospace polymers like PEEK, or if we look in the side of amorphous, you will see there PAI or PI. A little bit below, you see PEI in the second level. If you are flying, if you look at the bin container over in an aircraft, that's most likely will be PI, meaning it's a high performance amorphous polymer. Now, what was our criteria to select the material? We studied at the base, and we studied with the material we were familiar. Cody mentioned that we started prototyping with stamp forming. There's a whole prototyping lab in the Composite Center. It's basically a full manufacturing cell for stamp forming. And the polymer we had available at that time and where we learned was a variation of PT, that is PTG, that makes it amorphous. And again, it's a fairly low temperature polymer, but it has the properties we need really to get a rebar. It's not probably the final product we would like to use for applications. We may choose other polymers. We have a number of options, but this was really a great way to get and demonstrate the concept of the rebar. The image here shows something that Cody described. On the left, we have what I will call a bar, no surface deformation. On the right, I will call that a rebar. Now we introduce the deformation. What we can see here is the mechanism, the rotating wheels that will create the denting, those lugs on the surface that are required to transfer shear stresses between the bar, the rebar now with the deformations, and the surrounding concrete. We have started conducting tests. I'm sharing some preliminary results. If these are not final values, we are looking at tensile strength and elastic modulus. If you are familiar with properties for thermoset rebar, you will see that these are on the lower side. Why? Because we are starting with tapes, the unidirectional prepregs that Cody explained, that are fairly, they're not I would say the highest fiber weight fraction that can be attained. They were more resin rich. That was good, really, because again, it facilitated the initial phase of prototyping. We also worked with a die that was a CNC in-house made of aluminum, allow us again to demonstrate the concept, but it's not the final type of die that will be used in production. The testing setup also, we are working on improvement of the grips. Many of the tension failures we have were the grips that, if you are familiar with ASTM standard, is not an allowable mode of failure. Again, these are, I would call, lower bound values, but allow us to do some preliminary design, prove the concept, and what we're working now is in enhancing the properties by having higher fiber content in the bars, by starting with a feedstock with higher fiber content, and improving the test gripping and methods so we can start publishing reliable data that can be used by designers. One good point I would like to mention is that when we did burn-off tests to see what's the fiber content of the bar, we got about the same value that was in the data sheets from the supplier of the feedstock material, the tapes. That meaning we really don't introduce any voids. We have really good consolidation. Those are great points and give us really the motivation to continue improving the product. We have done testing of beams to demonstrate how it works. And we look at two extremes. Tension control and compression control. Tension control, we force the beam to fail in tension. So we under-reinforce the beam. We don't put enough tension reinforcement, enough number of bars. Compression control, we force the beam to fail in compression by crashing the top concrete, meaning we put an excess of bars on the tension side. And again, the concrete now becomes the weaker part. What we did is we wanted to see if we can predict these failure modes. We went to the ASHTO guide spec for GFRP. We did a substitution of steel areas by FRP areas in our predictions. So the number that you see here, 16%, that will be the increase for the FRP compared to the same area of steel. It's not a big surprise because that area of steel was controlled by the yield of a steel, about 60 KSI. These are tension failure modes, and we're getting failures here in the FRP in the range of 70 to 90 KSI. It's less than what I showed for the coupon test. Again, we would like to be able to reach in the beam test, in the tension failures, the same kind of strength that we have when we test individual coupons. I'm pointing to the areas of improvement, areas where we can continue to work. There are a number of tests that are required to come up with a full set of specifications for designing wheel bars. Here we have our bucket list. And some of these items are already in the works. So we are looking again at developing reliable data sheets with tensile strength and tensile modulus. We are looking at characterizing that bond interface between the bar and concrete, and then proceeding to determine what is the development length, what is the length of the bar embedded in the concrete that I need to develop the full capacity of the bar. Each of these is a set of tests. And then other items that, of course, are very important. What is the fire resistance? What is the fatigue life? Durability, particularly to chemicals like alkaline that can affect glass fibers. What is the long-term response under creep loading? And now the good part of the talk, I would invite Jake here to come and demonstrate how the bars can be bent.
Thank you, Roberto. So for those of you who have heard a lot of talking the last few days, figured I would do something a little more exciting, which is bend some rebar and actually show you that it works. Because if it doesn't actually work, then we don't really have anything to actually show you guys. So pardon me 1 second, I'm going to plug this in. So part of what I want to help show you guys is that this process isn't some sort of super complicated fine-tuned process. I would say if you can cook a marshmallow successfully, you're probably qualified to make a successful bend. So a lot of things we've thought about: what's the temperature, how long, how much heat. Honestly, most of that stuff doesn't quite matter too much at the end of the day. I like to try to figure out a consistent heating width. So I usually grab about a glove width, mark it off. I'm just going to heat that much. As you can see, not super precise. The other thing you might notice here is I don't have a way to register temperature. Just by looking and feeling at the bar, I can get a pretty good feel for when it's ready to go. And that should take just about under a minute. Since the heat gun's been a little off and on, we'll see if it takes actually a minute or not. Now in this case, I'm holding the bar right over. Obviously, with a long piece, you couldn't do this. But in that case, you'd probably be moving the gun around. And this is only just a random piece of lab equipment that I pulled out of the instrumentation lab. It wasn't something we went and spec'd or looked particularly hard for. So again, it's really quite a simple process we're working with here. Now, one of the biggest challenges we had to overcome with this is making sure we could get a smooth bend. Because as any of you know, with a long, thin structure, when you try to bend it, you're gonna end up with buckling in it. What we have been doing is applying just a light little twist in it. And is there a specific amount? Not particularly, just enough. Helps result in a lot smoother bend. Now for the last part, we kind of need sort of a jig to help us bend around. So I brought with me a boring old pipe. I don't think any job site's going to be lacking for one of those. So at this point, I can start to wiggle the bar. I can see it flexing, and I know it's pretty close and ready to be tested. So all I'm going to do is just put a little bit of a twist in the bar, like so. Bring it around the pipe. And I'm going to hold it here for a good 10-15 seconds while it cools down a little bit. It'll take another 2 to 3 minutes before it's actually solid, but it'll hold its shape after just a couple seconds. So as you can see here, we have a nice smooth bend, maintaining most of the cross section. I'm sure at the end, if you guys want to come up and take a look at it, it'll be up here for everyone to see. Thank you.